GCD. It stands for Greatest Common Divisor. So what is it? Okay, so given two numbers, right, for example 12 and 30, there are many divisors which are common between them. For example, take the number 2. 12 can be written as 2 times 6. And 30 can be written as 2 times 15. And 12 can be written as 3 times 4. 30 can be written as 3 times 10. And if you are shrewd, you can see that the number 6 also divides both of them. Okay, 6 times 2, and here it is 6 times 5. Is there any number which is greater than 6 that divides both of them? The answer is no. I mean, you can try from like 7, whatever. None of them divides both of them without reminders. The reason is 12 can be written as 2 times 2 times 3. Focus that I am decomposing this number into product of primes. Okay, 2 is a prime number, 3 is a prime number. So what is a prime? A prime number is a number which does not have any divisors. For example, 11, 19, 17. Okay, and yeah, I can go on, but that's the reason, right? So it doesn't have any common divisors. And 30 can be written as 2 times 3 times 5. So we just take the common factors out of them. If there are multiple 2's or multiple primes common, we can take them also. And we just take the multiple common factors in between two of them and we multiply them together. Okay, so the common factor will be 2 times 3, which is 6. Again, okay, so we are interested in GCD with respect to a prime number, especially when you're talking about this SECP 256K1 implementation. Why? And the GCD of any number x and p, okay, so GCD of x comma p will always be 1 provided x is less than p greater than 0. Like, remember that in modular arithmetic we are only interested in reminders. Okay, so it doesn't matter if x bar is any number which might be bigger than p or smaller than p, whatever. We are only interested, even the negative number, okay, even negative integer, x bar could be a negative integer. We are only interested in this form. Okay, the form is that x should be less than p and greater than 0. It's a positive number which is less than p. So since none of the number which is less than p, none of the positive integer less than p divides p, we can conclude that GCD of x comma p will always be 1. Why is that useful? It is useful because of the multiplicative inverse. I will come to that. Okay, so the thing is that GCD has a special form. The thing is, if GCD of a comma b, a and b can be any numbers. Okay, doesn't have to be prime. Can be written in this form of a times x plus b times y. These x and y, they are called Bézout coefficients. This special form is called a linear form because we doesn't have any exponents with respect to a and b. We don't have this a square or b square or b cube, these kind of terms in this equation. So that's why this is called a linear form of the GCD. And GCD of x comma p, we know that it should be 1, and we also know that x can be written in, x comma p can be written as some x bar plus p into y bar. Okay, I'm just replacing the coefficients with x dash and y dash, right, since I have already used the symbol x for the previous slide. So we can write it in this form. What does this states? Just take a look at this. Okay, so we are able to write it in this form. Now from this we can conclude that x dash is the multiplicative inverse of x with respect to mod p. Take a moment, because from this basically we can conclude x times x bar is congruent to 1 mod p. Why? I mean, if A is congruent to, so if A is congruent to B mod P, then we can write A as some quotient into P plus B. Okay. So consider this x times x bar as a single term. So we can write x times x dash, is congruent to 1 mod P. From this we can conclude that x bar is the multiplicative inverse of x because 1 is the identity element. Okay. Yeah, so this is how we are going to find and discuss the algorithms to find the multiplicative inverse, because we very much know the additive inverse, right? With respect to addition, the additive inverse is minus x, which is nothing but p minus x, because p is considered as a 0, okay, because anything divides by, divided by p with respect to modular arithmetic p, okay, because p minus x plus x is equal to p, which is congruent to 0 mod p. With respect to multiplicative inverse, we are going to work with GCD.